So for those of you that are just joining this recitation, you need to be baptized. Am I right? Yeah, because we can't take you to Africa if you're not baptized. We always go to Africa and come back. So I don't know how it's going to be like. How's this baptism going to go? Okay? But I'll see how to carry you guys along. The main point is we've done a lot of stuff in this recitation. So we have our own way of making calculations easy. So that by the time you add it to what you learn in the class, then everything becomes so clear you don't need to use your glasses anymore, remember? So those of you who came here with glasses, you're going to take them off pretty soon. You don't need them anymore after this recitation. Okay. So I will go over the inclined plane again. And, the last time in the class, I told you guys about the force on an inclined plane that brings everybody down, remember? I called it the spiritual force, okay? The force that nobody tells you about, okay? Then we're going to see what's going to happen when we add secular motion to the problem. A lot of things are going to change, okay? So what happens is, in the class, I had an inclined plane where I used this guy, this table. I don't know if my camera can see this, but I will. Zoom it out so you can see it. Okay, now it can see it, yeah. So I have this guy on the inclined plane standing there, and I asked this marker to wait for me. I'll be right back. And what happens? It goes right down, right? And I asked you guys, what brings it down? Why does it go right down? And somebody told me due to gravity. And I said that's 50% of the answer. That's half of the answer. So because when you have an object on an inclined plane, like this, we'll start here. Use a better marker. Gravity goes straight down, weight, which is mg. Here is theta. The normal force is perpendicular to the surface. Normal force, unlike a plane surface, where gravity and normal force are just opposing each other, okay? So gravity and normal force on a plane surface are opposite each other. On an inclined plane, they are different. They are not opposite each other. And I told you the secret is that the normal force is always at 90 degrees to the surface. Every time it's at 90 degrees to the surface, irrespective of how you incline the surface, okay? And your gravity is always down. And then, if I'm pulling this object up, there is frictional force down. And if the object is accelerating down or going down at constant speed, there is friction up, depending if the friction is in the surface or not. Then I asked, what brings this guy down? What's the force that brings it? These are all the forces I know. And I said it's not directly the weight, but it's a component of the weight. How? So I said for an inclined plane, we take our x-axis to be parallel to the inclined plane. So this is our inclined plane. So my x-axis is like this. My y-axis is like that. Is that okay? And then the weight is going down, mg. If here is theta, here is also theta. So if the weight is going down, mg is between the x and the y-axis. So the weight becomes a force that has components in the x and y-axis. Is that okay? So because of the choice of our x and y-axis, the weight becomes a force that is divided between the x and y-axis. So when you have a force in between the x and y-axis, you know you have an x component and a y component, right? So the weight has a y component and an x component. So it is the x component of the weight that tries to bring every object down, and that is mg sine theta. We call it the spiritual force, and mg cosine theta comes here. So mg cosine theta always balances your normal force, and mg sine theta becomes the force that always drags every object down. So when you're working any problem on an inclined plane, always remember there is an additional force of mg sine theta trying to drag the object down. And I told you guys, if an object is sitting on an inclined plane, it's not rolling down, then it means that the frictional force and mg sine theta are in equilibrium. They balance each other. Is that okay? Is that okay? So when I have an object sitting on an inclined plane and I say, what's the frictional force? It's just mg sine theta, because that's the force that's supposedly supposed to bring it down. But since it's not coming down, frictional force is holding it up. So that becomes a static frictional force. Is that okay? And if you want to accelerate the object upwards, so you have to go against friction, you have to go against mg sine theta before you can have that acceleration. Is that okay? So mg sine theta plays a key role here. But when we add circular motion, a lot of things are going to change, and I'll tell you what circular motion it's all about. So I'm going to take this back down. I'll probably zoom back in so that you guys can see this more clearly. I should probably zoom in all the way, and then I'll bring the board down. Yep. So we're good. Let me take this down. I'm still recording. I'm good. So what happens in a circular bank track is like this. So I have an inclined plane at some angle theta, and then this inclined plane is actually a circle. Aha! The whole story is going to change. So the first part of the story that will change is our x-axis comes back to normal x-axis, like this. Our y-axis comes back to normal y-axis, like that. So why is our x-axis and y-axis going to change to like this? Is because we are having a centripetal force now. There is a force in that direction. Is that okay? A centripetal force that goes to the center of the circle. That centripetal force that goes there it's not a force that acts directly there that we can put there, but it's a force that is a consequence of the normal force. So the normal force furnishes that centripetal force. And then I'm going to show you how this object now acts. So the normal force is still like this, Fn. Our weight is still going down, mg. But this time around, I have my centripetal force here. I'll call Fc. So this centripetal force is coming this way. But what is causing that centripetal force is two things. If I complete this guy here, okay, let me put this here. So here is also theta. Is that okay? So I have Fn sine theta, normal force sine theta coming here. Is that okay? And normal force cosine theta going up. Is that okay? Now I don't need mg sine theta anymore because I've changed. The weight is directly in the y-axis now. It has no component anymore. Is that okay? In this assumption. Is that okay? Are you getting that? So I don't need mg sine theta, mg cosine theta because the weight is in the y-axis and my centripetal force is going to be furnished by a component of the normal force here. Okay? Now, what's going to happen here is if there is no friction, is that okay? If there is no friction, in the absence of friction, there is only one speed you calculate. For the object to stay, if it's a car, you want this car to keep staying here without sliding up or down. There's only one speed if there's no friction. But if there is friction, there is a range of speeds. There is a minimum speed and there is a maximum speed. And that's the case you have today. When there is friction and you're asked to get the maximum speed. Is that okay? So what I'm going to do is I'm going to test you a little bit. I will give you the code to the quiz. I will explain to you the changes. See if you can on your own get that formula you need. I'll give you like 10-15 minutes. If you can't get it, then I'll go and derive it for you to see what's going on, and then you use the formula and you get it. And then you can do it by yourself. Is that okay? But I'm going to test you a little bit. I haven't understood this. So in the absence of friction, normal force sine theta is our centripetal force, mv squared over r. I call that equation 1. mg is normal force cosine theta. Normal force cosine theta balances mg. You see that now? So those are the two things I need now. Normal force sine theta gives that because there is no friction. If there was friction, I will resolve the friction to this direction also, and it will contribute to the centripetal force, either adding or subtracting. Is that okay? Depending on the direction. So that's the only trick. But now there is no friction. I don't care about friction. But if there was friction, I will do friction. Theta is here. Cosine theta. So friction cosine theta is acting here. Normal force sine theta is acting here. Both of them combined equals centripetal force, mv squared over r. Is that okay? That's going to be one of your equations. Is that okay? So be careful. See if you can do it. I'll give you. But if there's no friction, this is easy. So all you need to do is divide equation 1 by equation 2. Normal force sine theta over normal force cosine theta equals mv squared over r divided by mg. Normal force cancels normal force. Sine theta over cosine theta is tan theta equals v squared over rg. when the m's cancel. Is that okay? So this is when there is no friction. So if there is friction, the speed you're going to get can be maximum or can be minimum. But now they want the maximum one. So why is it maximum or minimum? If you're on a banked road and you move too slow, you will be sliding down to the center. Is that okay? If you move too fast, you slide up and skid off the plane. Is that okay? But there is a particular speed you move, or range of speeds if there is friction, that you stay on track. You don't go up or down. Is that okay? You stay on track. And that's what we're about to calculate. So the code for the quiz is Uniform Circular Motion, UCM. I think it's all lowercase. So UCM is the code of the quiz. So see if you can use the idea of what I have just changed to get some formula for the maximum speed. It's kind of a little tricky. But if you can't get it, I'll give you 10 minutes. After 10 minutes you can't get it, I'll derive it on the board. It's like just half a page. And then you see how clear it is. Okay? Yeah. Thank you. UCM. Is that not working? Yeah. Oh, thank goodness. So the first thing I'm going to do is, this is the problem. So am I asked for the maximum speed or the minimum speed? Maximum speed. So let's say this is a car that's going up here. Yeah, just to make it look fun. So this guy is going around this track. So don't forget, it's not an inclined plane, it's a... Okay? Remember, okay? So what happens is, my normal force is like this. My weight is like that. My centripetal force is going to be in this direction. This is theta, okay? My frictional force is going to be like this, because for maximum, I don't want it to go up, right? So it's trying to go up. Is that okay? For minimum, I don't want it to go down. My friction will be the opposite direction. Is that okay? So for maximum, my friction is like this. Here is also theta. And I draw this angle, and here is also theta. Is that okay? And then my problem is solved. So the frictional force, cosine theta, plus normal force sine theta, equals mv squared over r. I call that equation 1. Do we all understand that? Let me bring this right here, because I want to focus on that one. So do we all, is this okay with us? Frictional force cosine theta plus normal force sine theta is what furnishes the centripetal force, mv squared over r. Is that okay? Are we good with that? Yes.
And we're using the theta, that's right.
Yeah, this theta for this theta. So what I did is this. So if I have any line coming like this theta and this theta are the same. So that's what's happening here. That's what that theta. Is that okay? So but the line didn't touch the inclined plane, so you wouldn't know. Yes.
So is the centripetal force facing the opposite direction of the frictional force?
No, the centripetal force is going like this. So the centripetal force, now let me explain, that's a very good question. The centripetal force is not a force on its own that's staying there. No. It's a force due to a combination of the normal force components along this axis and frictional force. So they add to the centripetal force. So the centripetal force is not here because they won't be in equilibrium, right? Because three of them are in the same direction and there will be no equilibrium, right? So the centripetal force is not a physical force that stays there, no. It's a force that comes as a result of other forces in that direction. Do you understand? Is that okay now? So the normal force sine theta, the frictional force cosine theta, that is what brings about the centripetal force. A good way to understand centripetal force is when you have an atom, an electron going around the nucleus. Is that okay? So what keeps the electron around the nucleus is the Coulombic force, the electron attraction to the nucleus, to the hydrogen atom. So there is one proton, there is one electron. There is a force between them. Is that okay? That force that is attracting the electron to the atom equals the centripetal force. So it doesn't mean there is a centripetal force acting separately. No. It is that force that makes the object to stay in a circle with the centripetal acceleration. Is that okay? Is that okay? So this is that. Now we go to the y-axis, and then we're done. So what happens in the y-axis? In the y-axis, normal force cosine theta. What do I have here? Equals frictional force sine theta plus mg, because both are going down. Is that okay? So frictional force sine theta will be going down, mg is going down. Both of those we add to normal force cosine theta going up. Is that okay? Is that okay? And you are done. So this is just what I wanted you guys to get. So this is equation 2. So the next step is solve for m in 2. Solve for mass here. So let's solve for mass there. Solving for mass there, I have normal force cosine theta minus frictional force sine theta equals mg. So what is m? Is normal force cosine theta minus frictional force sine theta over g. So that's my mass, my m. I call it equation 3. So I put this m in 1. Is that okay? Is that okay? I solve m from 2, I put it in 1. So putting 3 in 1, what do I get? F cosine theta plus normal force sine theta equals v squared over r times m. What is my m? Normal force cosine theta minus f sine theta all over g. Is that okay now? I just put that as m there. Are we getting that? Okay. So we come here. This is where I started from. Let me make sure I got this. Yep, I get it. So we're good. So frictional force cosine theta, normal force sine theta equals centripetal force, mv squared over r. We understand this, right? Is that okay? And then frictional force sine theta is coming down, plus the weight going down, mg equals normal force cos theta going up. Is that okay? That's equilibrium in that axis. Is that okay? And then these are the equations we solve. So I say solve for mass in 2. Solve for mass here. Solving for mass here, what do we get? We get mg equals normal force cosine theta minus frictional force sine theta. So what is mass? Is normal force cosine theta minus frictional force sine theta all over g. So I call this equation 3, and I say put 3 in 1 for mass. Is that okay? That's the next step. So my 1 becomes frictional force cosine theta plus normal force sine theta equals m. Instead of m, I have normal force cosine theta minus frictional force sine theta all over g multiplied by v squared over r. Is that okay? So I just put m to be that. So that's mv squared over r. Is that okay? So this is where I now replace the frictional force by mu times normal force. Is that okay? So here becomes mu normal force cosine theta plus normal force sine theta. So I'm doing that because frictional force over normal force is the coefficient of static friction or kinetic friction depending on the situation. So frictional force is mu normal force. So I put that here for frictional force. So mu normal force is frictional force. Plus normal force stays the same. Equals normal force cosine theta minus mu normal force sine theta over g. All this multiplying v squared over r. So now I can cancel normal force from every term. Is that okay? Is that okay? Now I can cancel normal force from every term. I don't need the normal force anymore. So what do I have? So I'm going to get mu cos theta, is that okay? Plus sine theta equals cos theta minus mu sine theta multiplied v squared over rg. Is that okay? Is that okay? Yes.
Do you just get rid of the normal force?
Yes, because it's in every term, so I can cancel it out. So it's like dividing the whole equation by normal force. It's going to cancel out every time. Is that okay? Now what happens here? V squared equals Rg times sine theta plus mu cos theta, because they are adding, I can switch them around, over cos theta minus mu sine theta. So this is the formula we want for the maximum speed. So this is the maximum speed, V max. When you do the same thing for the minimum speed by just flipping this friction direction to this side, is that okay? You're going to get the same formula with sign change. So V minimum, you can try that, square is Rg into sine theta minus mu cos theta all over cos theta plus mu sine theta. So you just got lucky because you did V squared over Rg, but it so happens that this other part that you're supposed to do was a little close to your the answer, kind of. Okay? So you are given the angle and you are given mu, you are given the radius, and you have g. That's all you need to get the maximum speed. But don't forget it's square. So anything you get the square root of that. That will give you your real maximum speed. Don't forget to take a square root after, okay? And let me know what you get. Have a good one.